All right, before we start section 4.5, our warm-up, first one says, what is a line of best fit? Anybody describe it to me? No. Question 1 is separate from question 2.
Oh.
So question 1 just asks, what is a line of best fit?
Straight line.
Good. A linear equation, good, that models data from a scatter plot is how I would word it. But yes, usually it would be a line that would go through the middle of our data. So a line or a linear equation that goes through the middle of a scatter plot, that would be an easy way, kind of in your own words, to describe that. Okay, you could say a linear equation that models data. That would be a more mathematical or more technical way of putting it. Either of those get the same idea across? On number 2, for each one of these scatter plots, no, I do not expect that you are going to copy down these scatter plots. We are just going to talk about what type of correlation we see. Lydia, the first one is a negative correlation. We could put a line that roughly goes through the middle of that data that would have a negative slope. What about the second one, Jaisha?
0.
0 or no correlation. Okay, there's not really a good line that would fit through there. James, what about the last one? Positive. Good. We could put a line through the middle of all of that. That would have a positive slope, so positive correlation. Questions about our warm-ups? Concerns? Nothing? Okay. Section 4.5 is about analyzing lines of best fit. So we are going to use residuals, we'll define that in a minute, to determine how well lines of best fit model data. So we're going to see how good are these lines at predicting what is going to happen. First up, we've got residuals. A residual is the difference of the y value of a data point and the corresponding y value found using the line of best fit. Residuals can be positive, negative, or 0. So you might want to write down that we are going to take an actual data point or number from the data minus the projected value. So actual data value minus projected value, and that projected value comes from that line of fit. Finding these residuals gives us an idea of how well the line actually models the data. An expert claims that the equation y equals negative 2x plus 20 models the data in the table shown. Is the model a good fit? Now, in order to make this decision, we've got a little bit of work to do. So, we are going to essentially add another column onto this chart. And this is going to be y from the equation. So we're still going to be using the same x values, but now we're going to come up with new y values from the equation. And after we do that, we're going to be able to make yet another box on the end. That's going to be our residual values. Can't quite fit that in. That last box, oh, I didn't make it quite big enough either. That last box is going to be our residuals. Oh, box there, closer. We'll just call them R for now, residual values. This process is not hard, but it is time consuming. So we do have 8 different x values. All 8 of those have to get plugged in one at a time into our equation. Okay, so off to the side where I'm showing my work, my first one's going to be y equals -2 times, what am I plugging in for x first? A 1. Plus 20. What's -2 times 1? -2 plus 20 is 18. So my y from the equation for that is 18. Then we go down to the next one. Now what is my x going to be? 2. Okay, -2 times 2 is -4. Then we add 20. 16. So we could fill that in on the table. Next up, what are we plugging in? 2 times 3. What's -2 times 3? -6 plus 20 is 14. Do we get the idea of what we're doing here? We got to plug in all of these x values into this equation one at a time. Yes, I expect that you would show your work on this just like I'm doing up here. It does not take that long to write out. So what am I plugging in next? 4. -2 times 4. -8 plus 20.
Wait, where did you leave the 20?
So the plus 20 was in the equation, just like the -2 was.
Okay.
Okay? -8 plus 20 is 12. Put that in my table. Next, I'm plugging in 5. -2 times 5. -10 plus 20 is what? 10? We're getting close. Next, I'm plugging in what? 6. -2 times 6. -12 plus 20. Dominic?
8.
8, good. Okay, a couple more. I'm gonna move down below here since I'm running out of space.
We have to do all these.
Yep, I know, it's not hard, but it does take a little while to do. So the next one we're plugging in is 7. -2 times 7. -14 plus 20.
Oh my. Okay.
6. Last, we're plugging in 8. Okay, negative 2 times 8.
16.
Negative 16 plus 20 is 4. Okay, 6. Down there is a 4. Questions about finding those y values? It's really nothing new. We're just adding that step to this problem. All right, next up, we have to find our residuals, or our R values. We find those when we take the actual data number, so the sales number that they gave us, actual data, minus our projected value that we got from the equation. So first up, we've got 19 minus 18. What does that give me? 1. All right, 15 minus 16. 15 minus 16? Negative 1. All right, what about the next one? 13 minus 14? Negative 1. 11 minus 12? Negative 1. 10 minus 10? 0. 8 minus 8? 0. 7 minus 6? And 5 minus 4? 1. Okay, when we look at our residuals, if we are trying to figure out if this is a good model, we want our residuals to kind of add up to a 0 or cancel each other out or balance each other. Okay, so the closer we end up being to a 0 overall, the better. Okay, so if we look at this, 1 and negative 1, those can kind of cancel each other out. We've got 2 negative 1s here, which is nice because what else do we have lower? 2 positive 1s. So do we see how we can kind of pair these up to cross them out? Those 2 cross out. The zeros wouldn't really matter. This negative 1 and this positive 1 cancel out. This negative, this positive cancel out. So it's nicely balanced with positive and negative 1s and zeros. That means that yes, it is a good fit. So even though our answer is just like a yes, it's a good fit. If you don't have all of this shown to support that answer, then you're not getting points on a test or a quiz or homework, anything like that. Dominic.
Are we supposed to do like this and this and this, like you like cancel these out?
You don't actually have to write it on your paper unless it helps you to see it, but I should see all the work shown and I should see these columns filled in. Lydia?
Why did you cross them out?
Just to make sure that it was balanced. So positives balanced out with negatives. So if I could pair up a positive and a negative 1, those balance each other out.
Do they have to be like?
If it's not going to be balanced, it's not going to be a good model. They don't necessarily have to be positive and negative 1s. There are other problems where the R values or residuals are decimals or fractions, things like that. But you want them to balance each other out with the positives and negatives. If you had all your residuals as negative numbers, then your model probably overestimates. If all of your R values were positive numbers, then your residual or your line of best fit probably underestimates. Because we kind of have it balanced out with some positive, some negative, some 0, that means our line goes through the middle pretty well. Yes, ma'am.
So in order for it to be yes, it has to have negative and positive?
Right. Yep. Unless they were all 0, then it's a perfect fit. But yes, if it's going to have positives, it would have to have negatives to balance it out. Questions, concerns? These have all been good questions. Okay. We'll continue on. The table shows the ages X and the salaries Y of 8 employees at a company. The equation Y equals 0.2x plus 38 models the data. Is it a good fit? So again, on this one, we are going to be plugging all of our x's into this equation to figure out what our other y's would be. So I'm going to add another couple boxes onto this table. So we would have boxes for our y values that we get when we plug into the equation. And we are going to have boxes for our residual values when we subtract. Now, this type of problem, it might be a little easier if you have a calculator. It's not necessarily a requirement. I'll show the first one just to give you an idea of what we're doing here. What's the first x we're going to plug in? 35 plus 38. Okay, so if we take 0.2 times 35, does anybody know what we get? Dominic?
7.
Good. This is where a calculator could come in handy. And then when we add 38 to that, what do we get? 45. So that's going in my y value here. Then if I were to go ahead and calculate that residual value, I'm taking 42 minus 45. What do I get? -42 minus 45? -3. Okay, so we're doing the same kind of thing we did last time. If you want to find all your y's and then go back through and do your residuals, that's fine. But I'm going to give you a minute to start doing your calculations. And we'll do these, we'll fill the rest of this in together in a minute. What's the next value I should be plugging in to my equation after I do 35? Good. 37 is what's up next. Anybody get 0.2 times 37? So one way you can do this, which if you don't have a calculator, is just to take 37 times 2 or 37 plus 37. You should get 74. And since it was 0.2 instead of just a regular 2, you just put one decimal place back in there. So we end up with 7.4 plus 38 gives us 45.4. All right, after we plug in 37, what do I want to plug in next? What's my next x? 41. 41 times 0.2.
46.1.
Well, let's just multiply by 0.2 first. Dominic?
8.2.
Good, 8.2. And then we add the 38, we get 46.2. Okay, I understand this is a long process, but it shouldn't be a challenging one, especially if we have a calculator to help us out. What am I plugging in next? 43 multiplied by 0.2. $8.6, add to 38. Good. All right, next up, what am I plugging in? 45. 45 times 0.2. is 9 plus 38, 47. All right, after that we plug in what are we plugging in? We just did 45. 47 times 0.2. 9.4 plus 38. 47.4. Okay. Keep it going. Next, we're plugging in 53 times 0.2 is what? 10.6 plus 38. 48.6. Now I'm hearing the same few people answering throughout this. All of you are going to need to be able to do this, especially come Friday. So if you're not sure how to do this or you're not getting these examples filled in, I would change up how you're approaching this. Last thing I'm plugging in is 55. 55 times 0.2 is 11 plus 38 is 49. Now that we found all of our projected y values, we can finish finding our residuals, which means we are taking y from the actual data minus the y's that we found. So 44 minus 45.4. Negative 1.4. 47 minus 46.2. It would be positive 0.8. 50 minus 46.6 would be positive 3.4. 52 minus 47, positive 5. 51 minus 47.4, 2.6. 49 minus 48.6. Oh, that's not 2.6, 3.6, right? Yeah. Okay, thank you. All right, 49 minus 48.6, 0.4, and 45 minus 49, negative 4. Now, the goal here is to be able to cancel numbers out. It does not have to necessarily be one number cancels with another number exactly. For example, if I were to add 3.6 with the positive 0.4, what would that give me? A positive 4, and that could cancel out with the negative 4. So these three boxes all work together to kind of cancel each other out. Okay? But then if we look at what's left, the the negative 3 is going to come close to canceling out with what? The negative 3 would come close to canceling out with what? The 3.4. That would be close. We'd have a little bit positive left over. But would a 5.8 come close or evenly cancel out with a negative 1.4? What do we think? No. We are going to be way over on the positive side. This is not going to come close to evening out. So do we think that it is a good fit? No, not a good fit. Okay. And if you wanted to get really specific, you could just straight add these numbers across and see how close it ends up to 0. In this case, it's going to end up closer to 5 than 0. That's too big. It's not close to 0. Not a good fit. Questions about how we decide if it's a good fit or not? I totally get this process isn't super exciting and it takes a minute to do, but that's what today's lesson is all about, is deciding if these models that we're coming up with are good or bad fits for our data. Anybody need more time with this slide up? Okay. One more that's the same type of problem. We have the attendance in thousands of people at an amusement park from 2005 to 2014, where x equals 0 represents the year 2005. And then they just count up the years from there. The equation y equals negative 9.8x plus 850 models the data. Is it a good fit? So same thing we've been doing. I want you to try to do it on your own. I'll add a couple more boxes down here to our table. One for finding our y's and another one for finding our residuals. So these are going to be the y's from the equation. The bottom one will be residuals after we do our subtracting of the actual data minus the number we came up with. You might want to make your boxes a little bit bigger or write a little bit smaller since we've got numbers in the hundreds. So I'll set up my base of it over here. We're using that formula. What's the first thing I would be plugging into x? A 0 plus 850. Ooh, I ran myself out of room. Try that again. 9.8 times 0 plus 850. And of course, negative 9.8 times 0 is... Dominic? Nada, nothing, zilch, 0. And so when we add 850 to that, what do we end up with? 850. That means our first residual is what?
0.
0. 850 minus 850 is 0. Okay, so much like we were doing on the last problem and the one before that, yes, it's kind of time consuming, maybe a little tedious or boring. But we got to plug in these x's one at a time to find our actual or our projected y values, subtract them from the actual y values, and then we will be able to decide if we have a good fit. All right, I didn't write out the work for every single one of these because it ends up being about the same every time, right? So I wrote out the work for some of them. This is the work I'd expect to see. And I finished filling in the y values. So we just need to find our residual values, which means we subtract the actual data, which is on top, minus the y value we found. So what's our next residual? 4.8. Okay, the one after that? Negative 2.4. After that? Negative what? 81? 798 minus 820.6. I'm getting negative 22.6.
Yeah.
Okay. The next one, that one's pretty easy to calculate. Negative 10.8. The one after that. I think the next one should be like negative 9. Right? Okay, 785 minus 791.2. Negative 6. So far, is this seeming like it's going to be a good fit? No, we got a lot of really negative numbers. Okay, and only like one positive. So let's see if we can turn it around down here. It's going to really have to compensate down here. My next one is nope, still a negative 0.4. The one after that, 3.4. Okay, at least it's positive. And the last one? Negative 1.8. So based on this, do we think this is going to be a good fit? No. Do we even need to like add them all up? Not really, because pretty much all of them are negative. So I would say that overall this is really overestimating what the attendance is going to be. So I would say overall, no, not a good fit. Okay, questions about example 3? Dominic?
Can I have like 30 more seconds?
Sure. So the last bit of our notes in that box, finding lines of best fit. Are we all back in our notes? Good. Graphing calculators use a method called linear regression to find the precise line of best fit, which provides the best model for the data. So there's no guessing, there's no us having to draw in a line. There is a graphing calculator way of doing it. The calculator often gives you an R value called the correlation coefficient. This is different from residuals. So this R is not talking about residuals. The calculator just happens to also call it an R value. It's called a correlation coefficient. This number ranges from -1 to 1 only. So whereas our R, residual R's, could be any number, these ones will only be between -1 to 1. If it's a -1, there is a strong negative correlation, meaning negative slope, and it's a good fit. If it's a +1, there's a strong positive correlation, so there is a good line, it has a positive slope to it. If R is equal to 0, there is truly no correlation. And really anything close to 0, we would say probably does not have a correlation. Need more time on this slide. These last examples should go pretty quick. Okay, let's go to our last examples. Determine whether the correlation coefficient is strong or weak, and positive or negative.
Strong.
So this one, I would say it's pretty strong. I would say it's more strong than weak. And would we say it's positive or negative?
Positive.
Good. Strong positive. The next one? Weak but negative. Okay, it's kind of close to 0. And the last one?
Weak positive. Strong.
Strong positive. It's really close to 1. Strong positive.